Hey, welcome to another day. All right, hope everyone's doing well. We're going to continue on with our lecture. We're going to finish up light today, and actually we're going to kind of finish up some stuff with the electron configuration in the atom, and then we're going to run back and talk about the periodic table and review a few things on there. So let's get right into it. So I want to talk about what's called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle. So what we're doing is we're taking what Bohr was talking about and those quantized energy levels, and Heisenberg expanded on that. And when he was working with electrons, he said an electron is both a particle and a wave. It has a duality just like light, okay, just like electromagnetic radiation. So Heisenberg, and his first name is Warner, concluded that it is impossible to know both the exact position and momentum of a wave particle. So what he was saying was this. Okay, so if I have these are photons, okay, but he applied it to the electron. In order to find the photons where it is, we would actually have to stop it to find where it is. Okay? And as soon as we stop it, okay, we don't know what its momentum was. The other thing he said was this: to find its momentum, or its velocity really, okay, it's not going to be in one place. All right? So as soon as I measure its velocity, I don't know where it is anymore. Okay? So he comes up with this idea, or this idea, and he put it into mathematics. For a particle with mass, mathematically, he came up with this: delta x times m, which is mass, times delta v equals h over 4 pi. Now, you're not going to use this equation. I guarantee you're not going to use this equation, but you do need to understand what it's saying a little bit. All right, so let's label a couple things so you know what these are. H is Planck's constant. This delta x, or change in x, is the uncertainty of the position of the particle. Mass And our delta V is the uncertainty of speed or the momentum. So if we look at this equation, okay, it's giving us a relationship, okay, between the uncertainty of our position and the uncertainty of our momentum of a particle with mass. All right, so if we look at this number over here, this number is never going to change. Planck's constant's always the same, 4 pi. This number does not change. Okay. So if this number goes up, if we become more and more and more certain of the position, this number has to go down. So we become less and less certain of how fast it's going or its momentum. The vice versa is also true. The more we know about this, the more we know about this particle's momentum, the less we know about its position. Right? So this is just giving us mathematically what Heisenberg discovered. Right, so let's go ahead and write a couple things. So the more accurately we know the position, or delta x, of a particle, the less accurate accurately, I should say, we know about a particle's speed or momentum, which is our delta V. Right, so this is Heisenberg's principle. Now, this led into really the development of clouds, okay, the clouds around the nucleus. Okay, so Bohr, if we remember, he had specific paths. Okay, so the PELs were specific paths, okay, that the particles were doing around the nucleus. Okay, so the electron was going around and around and around and around. And this was going against what Heisenberg said, because in this model, we know the exact path that's going in. Okay, it's saying we know this exact path, and we don't. Okay, so this actually led into our next scientist that we're going to talk about in a minute. So let's write this. The uncertainty principle leads to the examination of wave motion on the atomic scale. And this is the beginning of what are called quantum mechanics. And this leads to the quantum model. In 1926, Erwin Schrödinger, S-C-H-R-O-D-I-N-G-E-R, there are umlauts over this, derived what's called the Schrödinger equation. and I'm going to give it to you. H, I don't even know what this Greek letter is, equals E. That's the Schrodinger equation. Actually, this is a simplified version of it. I'm going to tell you right now, you'll never use the Schrodinger equation either. All right, you just got to kind of understand what it says. All right, so this variable right here is wave function. When we apply this wave function to electrons, this gives us the probability of electrons. Probability of finding electrons. Again, you're never going to use it. You're never going to calculate anything with this. So what is it really saying? And that's what we got to talk about. What is Schrodinger really saying? Well, this equation, or this derived equation, is the basis of the quantum model. And what it's doing, it's changing the Bohr model, and the model describes that an atom has certain allowed quantities of energy. This is due to the allowed wave-like motion of an electron whose exact location is impossible to know. And what that's really telling us, or what it's really developing, are the electron clouds. And this whole thing is really coming from the Heisenberg uncertainty principle. So he develops what are called electron density diagrams. And these are areas of space where the probability of finding electrons around the nucleus is high. He's diagramming our clouds. That's what he's doing. Okay, the electron clouds. So if this is my nucleus, okay, that electron density diagram, okay, would look something like this. This would be my 1s orbital. Okay, it would be an area of space where the probability of finding electrons is high. Okay. Now he's saying also this. He's like, hey, look it. In this area right here, we could find electrons, but it's not probable. So he takes that Bohr model that was very specific on where the electron was and how it was moving, and he turns it into this, he bases it on Heisenberg, and we come up with this cloud model. Now what he's saying is, look at, I don't know where this electron is. Okay? I don't know where the electron is. It's somewhere in here, and I don't really know how it's moving. It could be going in a circle, like Bohr said, but it could be going brrrr. Okay? And the problem he has, again, is the more certain he is of where the electron is, so if he knows it's there, he doesn't know anything about its motion. He doesn't know if it's going to stay there. The more we know how it's moving, the less we know about where it is. All right? The less we know about where it is or where it would be. All right? So he uses his equation, and again, you don't really need to know that equation. All right? But from this mathematical equation, he comes up with these probabilities, and he makes the clouds. And that's really all you have to know about Schrodinger. Okay. Now, last person I want to talk about gave us a cool little equation. L.O. Lewis, Day, and this is French, and I have no idea how to pronounce it. Broglie? I don't know how to pronounce that. I probably should learn. Sorry, that was off the paper. So, what did Lewis do? He came up with the idea that, radiant energy could behave as though it were a stream of particles. He comes up with this idea that, like, light is really just a stream of particles. And those particles are photons in this case. Okay, so he's the one that came up with this idea that this is just a stream of particles. And then he applied it to matter. And he said, could matter possibly show properties of waves? He's the one that suggested the electron moving around the nucleus of the atom behaves like a wave. And if it behaves like a wave, that means it has a wavelength. So, because of this, the wavelength of any particle is wavelength equals h over mv. We know what h is. It's Planck's. M is mass, and v is velocity. Now, those of you that have had physics, if you take mass times velocity, we get momentum. So this is momentum. Now, for this equation, and you need to remember this, because you will be using this, mass must be in kilograms. And I'll tell you why. Because when we're getting energy, 1 joule is a kilogram dot meter squared over second squared. Okay, this is how we define a joule. Kilogram meter squared per second squared. Right, so your mass has to be in kilograms. Well, what can we do with this? Well, we can do some calculations. What is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6th meters per second? The mass of an electron is equal to 9.11 times 10 to the minus 31st kilograms. Now, wavelength equals h over mv. So wavelength equals 6.626 times 10 to the negative 34th joule seconds. So this is a parentheses. All over mass of 9.11 times 10 to the minus 31st kilograms times 5.97 times 10 to the 6 meters per second. Now, in this case, I got joules in here, okay, which is a problem. All right, so to get rid of that joules, okay, I can multiply this whole thing. We know that 1 joule is equal to 1 kilogram dot meter squared second squared. So I actually have to use this conversion also to actually get my wavelength. Okay, because Planck's constant is in joule seconds. That's what I've given it to you in. Okay, to get rid of that, we have to say 1 joule is equal to 1 kilogram dot meter squared second squared. And all this does is it gets rid of our joules, and this gives us our wavelength. Okay, so when we do this math, our wavelength ends up equaling 1.22 times 10 to the minus 10th meters. And are we okay with sig figs? Yep. Or you could say 0.122 nanometers. And that would be our wavelength of that electron. Now, just for fun. Okay, remember this equation works for any particle that has mass and is moving. So just for fun, I don't know how many of you play golf, but let's calculate the wavelength of a golf ball with a mass of 45.9 grams moving at 50.0 meters per second. Okay. So I hit a golf ball. Okay. It actually is going to have a wave-like motion. So we can calculate its wavelength. We know h, 6.626 times 10 to the minus 34th joule dot seconds. We know its mass. It's given to us in grams, so we have to put that in kilograms, which is 0.0459 kilograms times 50.0 meters per second. And again, we have joules in here, so we're going to do that same conversion. 1 joule is 1 kilogram dot meter squared second squared. So the wavelength of that golf ball while it's in flight is 2.89 times 10 to the minus 34th meters. Now, how big is that? It's extremely small. I mean, extremely, extremely small. It's so small we can't even observe that wavelength. Okay, we can't see it. We can't see that wave motion, all right? But it is there. Okay, so you could do this type of problem with anything. One year, I think I wrote a question, and I used, was teaching this during the World Series, and I used a baseball. Okay, when it was hit off of a bat, and we did the same thing. We had the mass of the baseball, and we had the velocity of the baseball after it was hit, and we actually calculated the wavelength that baseball had. Right? So it's kind of cool. All right. So you do have to use this one. All right, so we're going to kind of switch gears. This actually finishes chapter 6. And what I want to quickly do is we're going to go back into chapter 2. Okay, and I just want to do a quick periodic table review. And of course, okay, so we're just going to do a quick periodic table review of things that you should know from the periodic table and that kind of stuff. All right, so first of all, I want to review the metals. So on the periodic table, okay, the metals are left of the staircase. Okay, remember the staircase sits here. So all the metals are left of the staircase. Okay. And in my classes, we call this the whoop whoop. Yes, the whoop whoop. Why? Because it goes whoop, 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 and actually goes boop all the way across here. Okay, so we call that the whoop whoop, but it's the staircase, it's the dividing line of the periodic table. Everything to the left is a metal, everything to the right is a non-metal. All right, so now, some things about metals that you should remember. Properties. They're ductile, which means they can be drawn into wire. They're good conductors of heat and electricity. They're malleable, which means they can be pounded into shapes or just shaped. Okay, so when we're talking about malleable, that's an EA. I always think of a blacksmith pounding away at a piece of heated metal. All right, so metals are malleable. They're held together with metallic bonds. And remember, we described metallic bonds as a sea of mobile electrons. And we'll talk more about that this year. They lose electrons to form positive ions or cations. Okay, so all our metals always have positive oxidation numbers. Okay, so these always have positive oxidation numbers. They're lustrous, in other words, shiny. They have low electronegativity values. And low ionization energies.